Good morning, everyone. Can you hear me? Back? Great. So my name is Antonis Psaras. First of all, I would like to thank Bogdan for inviting me to do that presentation. There is a small change on the presentation that I'm going to present. The first one was about the large school increase, the main organization increase for 1,500,000 users. But a week before, we managed to finish the first ITSP integration and deployment based on OpenSIPS 2.1, so I thought that it's more relevant to that summit. So, as I said, I'm Antonis Psaras, I'm coming from Greece. The company that I'm working to is Microbase, I'm the managing partner, and in the next 2 minutes I will give you a really brief presentation on Microbase and who am I, and then I will present you the full case study that we had for deploying an ITSP carrier in Greece. Okay, so Microbase was founded in 2003. Basically, we are engineers. Most of those have certifications in several kind of IT and telecom parts, like DCAP for Digital Certified Asterisk Professionals, CEH Certified Ethical Hackers, CHFI Certified Computer Forensic Investigators, and so on. And basically what we are, we are a development company. We develop software. We're software developers. We started back in 2003 supporting carriers, and we've built the first postpaid billing in Greece, which was a convergent postpaid billing. We've built front management systems and generally value-added services for the customers. After that, we focused more on the Asterisk and OpenSIPS-based solutions, so we've built a product called ComServer, ComPlatform, which is basically a full IPPBX solution. We also presenting in Greece the product Excelsis, which is a contact center platform solution based on Asterisk as well, and the unified communication platform, security communication platform Labs, which is basically let's say an improved SBC from UK. These are our products: IPPBX solution, contact center solution, telecom services. We provide virtual PBX solution, call center on demand, premium platform for management of premium numbers and cost sharing, ePhone, which is a ITSP service, VoIP services. We do voice portals with Nuance, with voice recognition, and of course unified communication with OpenSIPS and Labs. But how do we use the OpenSIPS? These are the three main categories that we work with OpenSIPS. The first one is building carrier-grade solutions. We have a lot of carriers that we already built SBCs for them. We've built proxy, redirect servers, load balancer, registrar servers, and so on. We also use it to implement large services, large IPPBX services to large organizations. For example, universities. We have a university with 3,000 extensions. We delivered before a few months. The large installation that I told you before, the 1.5 million users, which is a collaboration network between all the schools in Greece and many other. And of course, we use it for security reasons in front, either from a normal IPPBX or a legacy IPPBX like Avaya, Alcatel, and so on. Few customers. INT is the largest insurance company in Greece. Vodafone, the largest mobile. Tripsta, a really big travel agency around the world. Connecticore, the largest wireless service provider in Greece. Pizza Fund, the largest delivery company. The municipality of Athens, the largest municipality in Greece. Insurance Market, Bulldog LV, Investment Bank of Greece, and CEH, which is the school network I told you before. These are a few customers of us. So what we do is we enter to the customer and we show them that OpenSIPS, Asterisk, and generally open source systems are good for them. So that's one case that we've did for the specific carrier that I told you. So let's see first the history, how we started. Initially, the carrier asked us to go there and build an Acme packets active-active clustering. I think that most of you know that the Acme packet now is bought from Oracle and it's supposed to be the best SBC in the market. So we were there, we started building the cluster, and during that, let me explain. First of all, they had an SBC cluster, an Acme SBC cluster, and they use a class 5 switch which is called Teles, and at the back they had a virtual infrastructure. The virtual PBX infrastructure was coming from Snow. So we had to deal with 3 heavily commercial products, where was, let's say, redesigned and stay there for a few more months before we start introducing the OpenSIPS. Now, when the carrier starts getting bigger, they had to do a lot of integration with other carriers, with other systems like the Portability systems and other third-party applications. So they realized that the big systems are not flexible. So there we introduced OpenSIPS. We've done a lot of tests. They realized that it's stable, and then we removed Teles and we put OpenSIPS as a proxy server. So what OpenSIPS is doing there is doing basically proxy things like number manipulation, permissions for their internal users, accounting, dynamic routing, and so on. Next step was to introduce media services. So, Asterisk. So we put an Asterisk cluster, so we were able to give, let's say, early media. For example, this number that you're calling does not exist, or the number you're calling will be charged 1 euro per minute, and so on. So that was the second step of open source on a really commercial-based environment on a carrier. And then starts having problems with the performance of Acme packets. Acme, from the series that we had to work, was doing something around 80 calls per minute, per second. That is really, really low for a carrier when you're supposed to have a few call centers where each one has about 200 calls per second. Okay, and a lot of failure calls. So we contact Acme, and the price was something around 300,000 euros to go to, let's say, 150, 200 calls per second. So, okay, let's try Acme as an SBC. Let's try OpenSIPS as an SBC and see what's happening. And they said, why not? Our proxy server is stable, let's do it. So we got OpenSIPS, a totally separated system that has all the call center on it and all the interconnections with the carriers, and we managed to get something around, I think it was something around 1,000 calls per second, handling RTP using RTP Proxy at that time. So we had a single box virtualized on a VMware with RTP Proxy, and we managed to handle around 1,000 concurrent calls. And that was the beginning. After that, they realized that OpenSIPS is something that they can rely on it. So we finally introduced them a full solution where we managed to remove all the Acme packet solution using OpenSIPS 2.1. And it's important that we used 2.1 because we had a number of problems with 1.11, where I will explain later. This is the design they had. That's the Acme packet cluster. We had a monitoring server here. So all the SIP signaling is coming to the monitoring server. That is the virtual PBX infrastructure. That is the OpenSIP in the middle. And then we have the sources outside, the data sources outside, the SQL cluster, MySQL cluster, and then we have the interconnection with FDAF. FDAF is basically the organization that keeping the portability information of each number. If you have got a number to Vodafone and you get the number and you get to go to another carrier, then there is a table where you have to look on it. This table has something around, I think it's more than 10 million records. I'm not sure about it. So it's a large table. And that's what we did today. This is the scheme that is going to be deployed 1 week after the summit. It's based on 2.1, and I know it's small, but basically we have a place here where we're handling the internal customers. So my customer with my link has an internal IP, because it's my customer, I don't want to give to go through public internet. So we have a place where we have the internal customers. We have a place where we have the customers that come in from the public internet and the call center, and then we have the carriers. In that way, we have a clean division between the type of customers, and we don't have any problems if something goes wrong. Just suppose that a predictive dialer from a call center is able to create about 1,000 calls per second if they need it. So if something happens and the OpenSIPS at the end is not able to support that, then all the enterprise customers will have a problem. In order to avoid that, we make these 3 changes. Moreover, this is a totally public internet infrastructure, so we will have hacking attempts, and we have to be more prepared for hacking incidents. All the SBC parts, and this is the new virtual PBX infrastructure that they have. So what the SBCs is doing is working on the perimeter, and they make sure that the traffic that is going in, it's the right one. This is just a proxy, an OpenSIPS proxy, which communicates with the outbound, with the outsourced data, like database clustering, Memcache DBs, NoSQL databases, FDAP communication, and so on. So this is the design that we end up. So, design overview, as I said, we're working with OpenSIPS 2.1, and explain later for a reason for that. We have a separated infrastructure for each type of customers, centralized proxy, working in a cluster for accounting, routing, and manipulation, high availability on proxies with active-active clustering, external high availability databases with MySQL clustering, Memcache DB clusters, and HTTP for backup, and we have enhanced security with fraud detection, sanity checking, and so on. Now on the SBC part, we use the Topology Hiding, the new feature of 2.1. We've had Topology Hiding before using the dialog module, but it wasn't that good as the Topology Hiding here. The one most important feature that we found was the ability to change the call ID. Because we had a few loops there, when you get the SBC, goes back to the proxy, and then from the proxy is going back to the SBC. So if the call ID is the same, we have a problem with the RTP. We have somehow changed the call ID. So the Topology Hiding with the call IDs, the call ID change, it's really working for us. And a small hint, if you configure the Topology Hiding, I don't know, did you do any workshop on Topology Hiding yesterday? No. Okay, today. When you configure the Topology Hiding, you put a password and a prefix. If that password and prefix is the same on the SBC and on the proxy, then you have a problem. Because the inbound proxy sees that call ID, identify it, and decrypt it. So you get the initial call ID that you have at the front SBC. So we had to have different prefixes and passwords. We also use Pike for DOS attack protection, call and rate limits, using the dialog profile and rate limit features, fraud detection, the new module. We have our own fraud detection logic. I'll show you a bit of it later. We use resource-based load balancing because we found out that the SBCs of the carriers are not able to support that number of calls per second. So we have an interconnection with the carrier with 4 Acme SBCs in order to support the traffic, the call center traffic that we're sending at the rate that we're sending it. And we also use UDP, TLS, TCP, and SRTP. So we moved from the RTP Proxy to the RTP Engine, and I'll explain later why. This is what the proxy is doing. It's more business, let's say, logic. We have the topology hiding again. We'll see later why. We have the clip and clear management. So, for example, one customer is able to make a call from a specific caller ID. So we have to make sure that this caller ID is from that customer. And if that customer is not sending any caller ID, we have to put one at the front because of the information that the other carrier should have. So one of the things that this module does is checks if you're sending the right one. If you don't, or if you try to send a caller ID restriction, then we put the P asserted ID, which is the caller ID of the customer, so the next customer, the next carrier will know exactly who is sending the call. So if this is a fraud call, or it's a, let's say, bad call, then they will be able to trace back the customer, even if it's an unknown, let's say, implementation. Number portability, this is a big thing, because each call's coming in, it has to be resolved and find out who is the right customer to route the call. So if my number is on Vodafone range, but I move to another carrier, then the carrier should know and send that number to the new carrier and not to the one before. More on that, there are some carriers that they're not able to do things like that. So if, for example, someone is sent a call to us and that number is not ours, we have to send back a 14 release. So they will realize that this number is not ours, but it's someone else. So they will go and look for the table after the first call is failed. Advice of charge. This is something that we found it back on 1.11 and there is not that back on 2.1. Basically what we do is at the end of the call, we send the advice of charge, so someone, let's say a hotel, will know exactly how much we will charge them. So they get that number, they put a profit, and then they put it on their billing, so they don't have to have a billing. So we implemented advice of charge on SIP. Of course, we use dynamic routing. I hear a really nice feature about the dynamic, the quality-based change of the priority. I'll check that very, very soon. And we do accounting. Let's see flow. That's the carrier, SBC, the core proxy, the intranet SBC. So here we have internal IPs. And that's the customer CP. So someone is calling from our interconnected carrier, goes to the core SBC, then to the intranet. So here we have a multi-home environment, then it goes to the customer, and then the RTP is established between those two RTP engines. Here, as you can see, we have a bridge, because we have internal and external IPs. This is an easy scenario. A more difficult scenario is the one coming where we have two customers on the internet. In that case, that customer is calling the internet SBC, that goes to the proxy, and the proxy sends the call back. In that case, if we didn't have the topology hiding here, and here, the OpenSIPS was able to handle the call, but we had a problem with the RTP. The RTP sees the same call ID, the RTP proxy sees the same call ID, so we had a problem. So what we do is we do topology hiding here and topology hiding here. So when the calls comes here, then this is shown as a new call. And what it really does, it's not doing that, but it's doing that. It goes back to the internal and then goes back. So this is working. And this is a performance test. 6,350. We do all the required functionalities like fraud checking, portability checking, number manipulation checking, and before sending back the call, we just reply back with the 404 that the number does not exist. Basically, what we tested here was the ability of the project to handle a large number of requests. So basically, we're able to handle 6,350 requests per second. A few script tips. Are we okay? Is there any question? Should I slow down? Great. Yes?
No, great.
Great. Okay. So basically, in order to have a clean script, we use the include file functionality, where we can include several config files that are putting routing blocks in our script. So when we have an invite for a new call, then that is what we write on the main script. So we have the check IP blocked. So there is another file having all the blocking logic. Authenticate call, manipulate, new user call, get the RTP flags, do the topology hiding, and then relay the packet. So all these are files separated together, so we have a really clean picture of the script that we write. And of course we have the reusability, because we have a lot of SBCs. For example, the number manipulation is something that will go to all SBCs, so we have to write it once. Another tip is that we used memcaching, local memcaching or Memcache server, in order to speed things up. So for example, here we use a local caching to cache the username and password during the registration, so we don't have to ask the database all the time for the username and password, we just cache it. For the portability, we use NoSQL or Memcache DBs, and we have two of those. So we have the first one. If the first one fails, then we go to the next one. And if that fails as well, then we don't have a network, so we do default routing. This is some fraud, let's say, detection. It's basically what we do here, and the most important thing that I want to mention on that slide is that when you realize that you have a fraud, don't let OpenSIPS handle that fraud. Demand from the IP tables or from your firewall to block that IP. Get that to the kernel level layer and start handling packets from that IP. So basically what we do here is we do something like we call ghost. So the friendly scanner UA, which is the user agent, is the SIP fishes. So if someone is scanning us with the SIP fishes, then we don't reply anything, and we store the IP of that client on a local database, and at the same time, we write on the log, fraud, that IP is blocked. At the same time, we're using fail to ban, and with that regular expression. So fail to ban gets that IP and block it from the IP tables directly. So basically, we have two. The SIP CLI is another scanner, and the friendly scanner is the SIP fishes. If someone tries to scan us, then will not find us, because we don't reply anything, even if we're open. Another trick that we did, it's on the registration. Basically, when someone is trying to break you, we'll start sending packets infinitely. Even if you block it on the IP tables, then they will continue sending packets, UDP packets, until they receive something. So this is a big pain in the ass, because yes, you block it, but you have all the traffic coming from there staying high. So what we did, okay, we found you, we have to block you, but at the last packet that you sent, we sent you, okay, you find the password, you got me. Okay, stop now. So they believe that they found the password, so they stop hacking. But at the same time, we have them blocked. Now, as I said before, we switched from RTP Proxy to RTP Engine. There are a few reasons for that. The one reason is that it's multi-threaded. We didn't have to use affinities to create many RTP engines. We didn't have to have many RTP engines running at the same time. We just have one process. It's multi-threaded. It performs very well. And again, they use IP table module. It's a kernel level module to handle the packets. So we have low CPU and low latency. A benchmark that we have for, I think it was 3,000 concurrent calls. On the same RTP proxy, we had 15% CPU usage on the virtual machine running on VMware. They have the ability to bridge between IPv6 and IPv4. This is something that is coming to the car here. They're going to have IPv6 customers and then route it to the IPv4 traffic. They have SRTP encryption decryption, which is very important, support for WebRTC, and it produces CDRs. That is very, very important. The accounting on OpenSIPS is not always accurate, because we're talking about signaling. If they don't get the pipe, if they don't get the signaling to stop accounting, then the number that you have in seconds is not correct. The RTP engine at the other end knows exactly what the RTP stops, so the CDR that they create are more accurate. So we do manipulation between those. Reason for using OpenSIPS 2.1, new improved design, better overall performance, very useful module from AsyncDB, Topology Hiding, REST client, and support for RTP Engine. And as a conclusion, OpenSIPS, it's a great product. Mature, stable, flexible, scalable, and open. You can really implement everything that you like. You just have to be very careful on the design, and using the new feature, I think that the puzzle is already completed. There are a few other features that they might imagine and create, but at that time, I think that the project is very, very mature, and you're able to implement whatever you like. That's all for me. I don't know if you have any questions. Thank you very, very much.